Warm-up question asks about magnetic force, gravitational force, and the electric force that are acting between the magnets shown in the picture. The magnets shown in the picture do show magnetic levitation, where you have one magnet floating on top of the other due to repulsion between them. So the first question, magnetic force on A due to B, is a repulsive force. That's why it's floating instead of attached, is because they're repelling one another. That means the bottom part of magnet A has to have the same polarity as the top part of magnet B. Maybe it's two souths facing each other, or maybe it's two norths facing each other, but that's what we have there. The second question I put in here because some of you were missing this in the assignment yesterday. Anytime you have two objects with mass, they have a gravitational force of attraction. Even if those two objects are magnets, even if those two objects are charged particles. Okay, if it has mass, then you're going to have gravitational attraction between them. So you can have and will have both magnetic attraction or repulsion depending on the polarity, and you could have gravitational attraction if there's mass, which pretty much everything has mass. And then the last one asks about the electric force, but it says that they're both neutral. So your electric force here, if they're both neutral, you don't have an electric force. You need to have a charge imbalance, like a positive attracts a negative, or two negatives repel, or whatever. So again, you can jot down whatever you need to from this, but we're going to get into notes today on electromagnetic induction. I need everybody to quiet down. Okay, we already know that moving electrical charges, which means a current, will generate a magnetic field. We've looked at the magnetic field that gets generated around a current-carrying wire. We saw it traced out with a compass as we moved it around in the simulation. But that leads us to another question. Is the opposite also true? Can magnetic fields generate electric current? And your answer to that question is yes. I got into it the other day when we were talking about the right-hand rule in a loop of wire that is put inside of a magnetic field. We looked at how you could have the current inducing a force, or you could have the force of rotating it inducing a current. We're going to talk about that today because that is one of the applications of electromagnetic induction, which is the production of voltage or electric potential difference across an electrical conductor in a changing magnetic field. Basically, you get to use a magnetic field to make electricity flow by changing or moving the magnetic field. It does require change to the magnetic field, which you're going to see in the examples today as well. So again, we don't have to watch the whole thing because we don't have time, but whenever he puts it through the coil with fewer loops, it doesn't give as big of a reading, and when he does it through the one with more loops, it gives you a bigger reading, and then a biggest one, of course, when you have the most loops. The other thing that he explained is that it only happens when the magnetic field's changing. Okay, so we're going to look at Faraday's law of induction and how a changing magnetic field can induce an electromotive force, which is abbreviated EMF, in a loop of wire. And again, you get this by moving them with respect to one another. Okay, so either moving a magnet toward the coil or moving the coil toward the magnet or rotating them or something where one of them is moving with respect to the other so that the field is changing. Or if you have a electromagnet where you can change the strength of your field, then doing that could also change your field, and that would induce current in the wire, which you saw as the galvanometer reading showing up on that tool. Again, electromotive force is what causes electrons to move and form a current. When we talked about circuits, we talked about how the battery, the voltage, provides the force, the push to move the electrons. That push now in this example is coming from a changing magnetic field instead, but that's your electromotive force. Faraday's initial experiment looked like this. He wound an iron ring with insulated wire on both sides. And on the left-hand side of the diagram, you can see that you have this thing hooked up to a battery. And when you turn the circuit on, you're going to get the same thing where you have a ping over here. Even though these two aren't directly connected to one another, by running current through a wire, we know that a wire carrying current generates a field. And if you coil it up, the fields add up together. So you get a magnetic field over here that then affects this wire. So even though this wire isn't directly attached to the first part, it's completely separate from the other circuit, the magnetic field that this one induces or creates is going to induce a current over here. But only when it's changing. So only when it's turned on or turned off. So the action of actually flipping the switch on and flipping the switch off is when you see the change. Okay, if it's just sitting there running, it's not going to do anything over here. It has to be a change. He repeated the experiment doing what I just showed you in the video, where he took a permanent magnet and moved it in and out of a coil of wire, and he noticed that it was only when the magnet was moving, where there was a change in the magnetic field, that we got a current reading. So here are the factors affecting induction. You're going to see these again tomorrow because you have a simulations assignment to complete, but you can write them down today as well. But the direction of the magnet's motion. So he's explained that in the video as well. Moving it into the coil versus out of the coil give you an opposite reading. Or if you were to flip the magnet around, which he didn't show, but you get to test tomorrow, same thing. That is going to affect the induction. The separation between the magnetic field and the wire loop, when they're closer together, your field is greater, and so you're going to get a greater reading than when they're farther apart. And then relative speed, if you move it quickly, same thing, the field's going to change faster, and that's going to give you a greater current reading. And the last thing is one he did show you, which is the number of loops in the coil of wire. More windings or more loops gives greater current. I do want to also mention this vocabulary term. A coil of wire where you have it wound on itself like that has a name. It is called a solenoid. Okay, so we're going to use that term when we're discussing those coils of wire. Here is a picture of a solenoid, a coil of wire around a nail, which this picture is actually showing an electromagnet. An electromagnet is when you use electric current flowing through a wire to create a magnetic field, and coiling that wire strengthens that magnetic field because it adds together, because now you have the field created by each of those loops of wire, all adding together. Electromagnets are stronger when your solenoid contains an iron core like this nail, as opposed to just an empty loop of wire. When you have more loops and when the current flowing through the solenoid increases. This is an application of that electromagnetic induction and Faraday's law that we were just talking about. So an electromagnet is one application of it. And I have a video clip showing somebody talking about electromagnets and the factors that affect their strength. But again, looking at that, it goes over some of the things, including the fact that the magnetic fields add up whenever you have a solenoid. So you get this field building on itself, but it's still not strong enough until you add some kind of ferromagnetic core. A nail, a bolt, something made out of iron, cobalt, or nickel is going to do that. And so when you do this, now this field can cause the domains in that material to align, and now you have a temporary magnet that can be turned on and off. Okay, so that's an electromagnet, and we looked at factors that affect the strength of them in that video clip. So questions that would show up on a multiple choice test, quiz, or assignment like today might look like this. Circle the strongest magnet in each of the following pairs. So here you're just comparing these two. Both of them have a 9-volt battery. They both have a solenoid with the same number of loops. The only difference is the one on the left is wrapped around a nail, and the one on the right is wrapped around a pencil. And so you're going to pick the one that's wrapped around the ferromagnetic core. A nail is made of steel, which is an alloy of iron, and so that's the one you would want. That would be stronger. Or you could compare these two. Again, this time they're both nails. This time they're both 9-volt batteries. The only difference is the number of loops. And in the video clip, he goes over this as well if you want to watch the whole thing. But more loops is going to give you a stronger electromagnet. And so the one with more windings is going to be the stronger one. So again, that's how that might show up in a multiple choice question. So electromagnets are just one application of electromagnetic induction. This is another one. Transformers. A transformer uses electromagnetic induction in order to step up or step down voltage output. An alternating current in a primary coil and creates a changing magnetic field within the core, and that induces voltage in the secondary coil. So basically what you're dealing with when you're dealing with a transformer is you have a situation where you have a voltage coming from some source that's either too high or too low to operate something. Like in your house, there's a transformer for your doorbell, because doorbells need like 5 volts, and your house, the outlets are like 120 volts. And so you have to step down the voltage for a doorbell. Or if you're traveling, you'll have different voltages overseas versus in the US, and so they'll have transformers built into the kits that they sell to make your plugs fit over there. They'll have a transformer built in because our voltage is 120 and over there it's 240. Okay, so you'll have to step down their voltage so that it doesn't burn up whatever you're trying to plug in. So anyway, these are the components: primary coil, secondary coil, and some kind of core. It looks like this. So a transformer, you're going to have some kind of core, and you're going to have wire wrapped around it, but you're going to have different number of loops of wire on the primary than the secondary. This is an example of a step-up transformer. You can tell it's a step-up transformer because it goes up in the number of loops, and thus it goes up in the amount of voltage. Okay, so this one has twice as many loops on the secondary coil, so if you put in like 100 volts, then you're going to get out twice as much. Okay, that's the math for this unit, by the way. It's proportions. You're going to see it again in a second. But a step-up transformer is going to increase your voltage using electromagnetic induction. A step-down transformer, exactly the opposite. You'll notice this time my secondary coil has half as many loops. So if you were to put in 100 volts this time, you'd get out 50. You'd get out half as much because it has half as many turns of wire. There's a video here if you want to watch it on slide 78, but we don't have time to watch this one, but it goes over transformers in more detail. You're welcome to open it up on your own. But this is what the math problems might look like. A portable X-ray unit has a step-up transformer, the 120 volt input of which is transformed to the 120,000 volt output needed by an X-ray tube. The primary coil has 50 loops. What is the number of loops in the secondary coil? If you're trying to step up your voltage from 120 to 120,000, that's 1,000 times more voltage. You're going to need 1,000 times more loops. But you can just set it up as a proportion. Okay, 120 to 120,000, 50 to x, and solve for x. If you're setting two fractions equal, cross multiply and then divide. So 120x equals 6 million, and then divide. There's your 50,000 loops, which of course is 1,000 times more than 50. That's the math for this unit, by the way. It's just proportions. So there's no other math other than this. All right, next application of electromagnetic induction is called a generator. It is a device that converts mechanical energy into electrical energy, and it does so by turning something. Most power plants turn a turbine, whether it's a wind turbine or a hydroelectric power plant turns a turbine because the water pushes it, or you can turn a crank by hand. Okay, but when you do that, you apply a force to a loop of wire, making it rotate in a magnetic field, and that creates a current in the wire. We looked at it yesterday with the right-hand rule and that loop of wire. You can use that force to get a current, okay, and you can figure out what direction it'll go, again, using the right-hand rule. A motor is similar, but it's exactly the opposite in terms of its definition. This device converts electrical energy into mechanical energy. So when you look at a motor, you're going to see a battery connected to something or some kind of voltage source running a current through a loop of wire in a magnetic field. This time, it's the current moving through the wire in the field that creates the rotation rather than the rotation creating the current. So they're exactly opposite of each other. You need to be able to recognize them by picture. Okay, so motors, you're going to see a battery or something powering that motor, causing the rotation. With the generator, you're going to see something that has to be turned, like a hand crank or a wind turbine or something. All right, that is it for today's notes, which I know we went through very quickly. You're welcome to go back through them on your own. You do have an assignment, 1302.4, electromagnetic induction problem set, which was initially due tonight, but because of the shortened period, we went ahead and said, hey, we'll set the due date for tomorrow. That said, you do have an assignment tomorrow, so keep that in mind. If I were you, I would probably try to get at least some of this done tonight so you're not trying to do both of them tomorrow. One more thing, I would recommend you bring headphones for class tomorrow if possible, because tomorrow's assignment has a couple of video clips built into it. So if you have headphones you can plug into your Chromebook, awesome, I would recommend it. You have a quiz on Thursday. Your test is next week, but you have practice you can work on in the unit summary, and if you want, there are some more notes on slides 84 to 99 that you're welcome to look at. All right, guys, you can either open this up, 1302.4, or you can work on it at home tonight, but it's due tomorrow.